thus far in our journey of acids and bases, we've talked about the characteristics of acids and bases, the difference between Arrhenius and Bronsted-Lowry acids and bases, how in general acids are going to give away or give up their hydrogen ion to the solution, and bases will either take the hydrogen ion to give away a hydroxide ion. So today we're just going to further our investigation of pH by talking about what pH actually measures, right? So if we put a pH meter into a solution, what is it actually measuring? What inside of the solution is the indicator or the pH meter actually measuring? So let's take a look. So our first question is, what is pH a measure of? So when you measure the pH of something, what are you actually measuring? So pH is a measurement of the hydrogen ion concentration. Okay, so it's how many hydrogen ions are floating there in the solution. That's what pH is. So those solutions with a low pH actually are what we call acidic. Remember, those are from 0 to 6 here. They are actually going to have high concentrations of hydrogen ions. So if we take a look here at the picture down on the bottom, we can see that, if we have a pH of 1, our hydrogen ion concentration is times 10 to the negative 1. Okay, versus, pH 6 has times 10 to the negative 6, which is a smaller number. Okay, so it's kind of weird to think about. It's kind of opposite in a way that low pH has high hydrogen ion concentrations. Okay, now those with high pHs, okay, that means that they're going to be basic over here on the basic level, are going to, remember we're talking about 8 through 14, those are high numbers on our pH scale. They're actually going to have low hydrogen ion concentrations, because if we see here, pH of 12 is going to have 1 times 10 to the negative 12 concentration of hydrogen ions. Okay, and so that's much smaller than the times 10 to the 1. Okay, so if we take a look at 14, a pH of 14 would have 10 to the negative 14, which is a much smaller number than times 10 to the negative 12. So we're going to investigate why there's the discrepancy between, why if you have a low pH level, it actually has high ion concentrations, and if you have a high pH number, it's actually low concentration of hydrogens. So we're going to investigate why, but for right now, that's what you need to know. Another interesting fact about pH is that it is a scale that goes by the power of 10. So what that means is that if the pH of a solution increases by 1, so if we go from pH 2 to pH 3, it actually is a decrease of the hydrogen ion concentration by a power of 10. Okay, so it's not a one-to-one thing. It's if you go from pH 2 to pH 3, you're decreasing the hydrogen ion concentrations by a power of 10. So let's see what that looks like. In the chart here, I've got pH on the left and I've got hydrogen ion concentration on the right. And these brackets here, when it's around a symbol, mean concentration. So the brackets are always going to represent concentration. And remember, our fancy chemistry word for concentration is molarity. Okay, so we can see in our picture here that we've got molarity, concentrations of our hydrogen ions. So if we take a look at the difference between pH 1 and pH 2, the hydrogen ion concentration of pH 1 is 0.1, whereas the hydrogen ion concentration of pH 2 is 0.01. So that's a whole, times 10 to the 1 difference. Okay, it's a tenfold difference. If we take a look again, between 3 and 4, we're going to go from 0.001 molarity, okay, down to 0.0001 molarity. Okay, so as we go up in number for pH, we are decreasing the hydrogen ion concentration by a power of 10. So when you get all the way down here to on the basic side, pH 10, okay, it means that there are 0.000000001 molarity or concentration of hydrogen ions. And if we drop down to pH 11, then it's 0.000000001. So it's a tenfold difference. We add another 0 right there. So when you get down to pH 14, it's a dramatic difference in hydrogen ion concentration between 0 and 14. So keep that in mind. Anytime something jumps in pH from, even if it's just one pH value, it's going to be a huge difference in hydrogen ion concentration. All right, the next thing we're going to talk about is something that's less common than pH, but it actually exists. There is a scale called the pOH scale. If pH measures hydrogen ion concentration, then pOH measures the hydroxide ion concentration in the solution. All right, so acids, okay, over here, and if we look on our picture, acids are going to have very low hydroxide concentrations. Okay, so if we take a look at the hydroxide concentration for pH 0, it's times 10 to the negative 14. That's a super small number. Okay, that's because he's got a ton of hydrogen ion concentrations. So pH and pOH go hand in hand. In fact, if you take a look at the what's it called, powers in this, we have 0 and 14. Okay. If we take a look between 6 and 8, 10 and 4, 12 to 2, 14 to 0, we're going to see that here pH plus pOH is always going to equal 14. Okay, so that's how we get our scale from 0 to 14, because the subscripts or the exponents are going to always equal 14 when we're relating pH and pOH. Okay, so again, pOH measures the hydroxide ion concentration in the solution. So acids are going to have low hydroxide ion concentrations. And so if we actually take their pOH values, their pOH will be high. Bases, on the other hand, okay, are going to have very high hydroxide ion concentrations. So if we see here, down here, for number 13, times 10 to the negative 1 is a much bigger number than 10 to the negative 14 that we saw up here. So bases down here are going to have high hydrogen ion concentrations. Okay, and so if it has a high hydroxide. So if it has a high hydroxide ion concentration, its pOH will be a low value. And again, we will see and kind of clarify that mathematically in the next question. All right, so if something is neutral, if it has a pH or a pOH of 7, okay, because on both scales it will both be a 7, because remember, pH plus pOH is 14, so 7 plus 7 is 14. So if a solution has a pH or a pOH of 7, it's neutral, remember? So what that means is that there's two scenarios. Either it has no hydrogen ions or hydroxide ions at all, or it has equal amounts of the two, so that they cancel out in order to read, 0 or nothing, like a neutral substance. Okay. All right. So that is the pOH scale. It exists, but is not used as much, obviously, as the pH scale, because that's probably the first time you've heard of the pOH scale. Okay, so now let's take a look and see mathematically why we have those opposites for pH and pOH. So why is a low pH have such a high concentration of hydrogen ions, and a very high value of pH, like 14, has very low concentration of hydrogen ions? So this discrepancy has to do with how we mathematically figure out or calculate the pH of a solution. So the pH of a solution is the negative log of the hydrogen ion concentration. And the pOH is the negative log of the hydroxide ion concentration. So when we put these numbers into our calculators and we do the negative log of them, a really low number for hydrogen ion concentration is going to end up being a big pH number. Okay, so let's take a look at some of examples, and we'll kind of see how it works. So here is example number 1. It says, what is the pH of a solution with a hydrogen ion concentration of 1 times 10 to the negative 4? Okay, so again, what we'll do is, pH equals negative log of our hydrogen ion concentration, right? And it's asking for pH, so that's the formula that we're going to use. So in our calculators, we're going to type in negative log, okay, of 1 times 10 to the negative 4. Okay, when you do that, you end up with a pH of 4. Okay, so if you plug in that negative log times 1 times 10 to the negative 4th, the pH ends up being 4. Okay, in fact, one of the ways that you can kind of do these pHs without really actually having a calculator is, here's the trick. It's usually just the negative value of the exponent for your concentration. So our exponent is negative 4, so that means the pH, okay, is 4. Now that usually only works if you have a 1 out here in front. But if you have a different number out front, the exponent is usually very close, and I'll show you another example. So if, like on a test, you're not allowed to use a calculator, or if you forgot your calculator or whatever, you can kind of do it a little cheater way by just taking the negative value of the exponent. So basically turning that exponent to a positive number. So that'll work, for the same kind of thing if we have, times 1.0 times 10 to the negative 13, okay, and we're asked to find the pH. Well, the pH would be 13, because we just take this and we take the negative value of it, so we'll just take away that negative sign, okay? So that's how mathematically the pH works. It's taking the negative log of either the hydrogen ion concentration or the hydroxide ion concentration. So let's take a look at another example. This one says, what is the pH of a solution with hydrogen ion concentration of 3.4 times 10 to the negative 4 molarity? So again, pH, remember, is negative log of the hydrogen ion concentration. So what we'll do is we'll take our negative log and we're going to just plug in our 3.4 times 10 to the negative 4th in your calculator. So if you actually do that in your calculator, what you'll end up with is a pH level of 3.47. Okay. So again, you can see that it wasn't, quite matching, perfectly up to the negative value of the exponent. Okay, so that's because this number out front here is not 1.0. It's a higher number, but it is very close. 3.4 and 4 is very close. Okay, so you can kind of check yourself with that. If you have an exponent of negative 4 and somehow you get a pH of 14, okay, you've done something extremely wrong. Okay, so the exponent values and the pH values should be pretty close. All right, let's take a look at one last example, and you'll be prepared to do a whole bunch more examples on your own tomorrow in class. Okay, so our last example is a little bit more tricky. It says, what is the pH of a solution with a hydroxide ion concentration of 2.6 times 10 to the negative 6? Okay, so we can't directly relate pH and the OH concentrations. So if we're given the hydroxide ion concentration, we have to find the pOH of the solution first. Okay, so that is going to be negative log of the hydroxide ion concentration. So if we plug that in, we're going to do negative log of 2.65 times 10 to the negative 6. And we're going to get a pOH of 5.58. Okay, and again, 5.58 is very close to 6, that value of our exponent. So we know it's probably correct. Now, this is pOH, though. We need to find pH. You always have to pay attention to what it is actually asking for in the question. Okay, so if we have pOH and we need to find pH, how are we going to do that? Well, the answer is that we are going to use the concept that we talked about earlier, where pH plus pOH equals 14. Right? We know that the pH of a solution plus the pOH of the solution must equal 14. So we can plug our pOH value in to the pOH here. And so if we solve for pH, we're going to have 14 minus, right, our pOH value. So if we do 14 minus 5.58, our answer is, we'll do a pH of 8.42. Okay, so that there is our final answer. So you need to always make sure that you are answering and solving for what is actually asked for in the question. Okay, so you will have a few of those tomorrow, so please don't get tricked up by them. Okay, so we'll see you tomorrow in class for some more problems.